Alright, now we'll be talking about neutron porosity. So, the neutron porosity tool is designed to measure the abundance of low energy neutrons in a formation. So, we want to get porosity, but our measurements will be more related to the content of hydrogen within a formation. Now we can say how to get or how to go from hydrogen in a formation to porosity units. Here we will see it. So that is the main principle. That is what our tool is measuring, hydrogen content. Let's see why. First of all, this is just about remembering you why are we doing this, or why are we running this tool. It is in order to get porosity, and with porosity we will put it into Archie's equation and we'll get water saturation, and after that hydrocarbon saturation. So one of the I highlighted this comment that you will see measurement from neutron porosity on clay. They will read high values for porosity, and this is why. As the amount of clay minerals within a formation increases, the neutron porosity tool will tend to overestimate the porosity in that formation. Why? As I told you before, the neutron tool responds to the hydrogen content in the formation. And a formation containing gas exhibits a neutron porosity that is much lower than the true porosity of the formation. Here we have an example of a log. Our neutron porosity is this -1, and you can see it here on shale. It's higher. Now when we have gas, it reads low. So you can run a neutron porosity tool in fresh water, salt water, oil base, even case hole. This is important. We'll be discussing the measurements on thermal neutron tool. There is another tool called pulse neutron tool, but that is a way different concept, or we will just be covering thermal neutrons. So the physics of measurements, I'll just say it one more time, that hydrogen is the most efficient element at causing this energy loss, the energy loss of neutrons, because the neutron tool, they use a chemical source. It will start to emit high energy neutrons that will start to interact with the formation. That neutron, as it travels from the radioactive source through the fluid in the borehole, through casing, through casing, or ether is casing, and through the formation, that neutron will start to make a bunch of collisions with all atoms in the formation. So with each collision, the energy level of that neutron will slow down, and it will go from high energy level to thermal energy level. Once the neutron is on a thermal level, the detectors will be able to read it or to see it. And this is a few comments on the nature of the radioactive source. It is made of americium and beryllium. This is just explaining you how that neutron is generated. This is how the radioactive source looks like. This is what I mean by thermal neutrons. This is the energy level. It must be lower than 0.1 electron volt. So these are a few more comments on how those collisions are from the moment that the neutron leaves the source until the moment it is perceived by the detectors. There are elastic collisions, the angle of collision. It is important on those interactions. And this is a key concept: the slowing down cross section and the capture cross section. So what is that? And you can see that hydrogen is on top of the list. So the probability that any nucleus will slow a fast neutron to a detectable thermal level is reflected by a slowing down cross section. So it is a probability. And the probability that an atom will capture a thermal neutron, that is called the capture cross section. Now let's talk about the detectors. All these things should be considered for making correction: the effect of the wormhole size, salinity, temperature, the standoff of the detectors. Here is an accessory of the tool. It's a decentralizer regarding the standoff. So here we have a nice picture. This is our Neutron tool, our decentralizer, and we can see two detectors. Whenever you see two detectors in any long tool, they are compensating for something. In this case, they are compensating for the standoff. Remember that the standoff is the physical distance between the formation and the detector. So at the end, the porosity is calculated based on the ratio of the counts of the slowest space detector and the longest space detector. And here we have the effect of different lithologies on porosity and the interaction of the neutrons. Standardization of units, the API, this is related to the way it is calibrated. On the top, the tool is placed within a water tank. If you're in the field, you will not see it. But if you're on the field, you should see the field verification, which is performed with some sort of block of known porosity. You should see the field engineer doing this, the field professional doing that. And that's pretty much it. Well, thank you for watching.